Welcome to this recitation session. हमारे पास जो agenda है, there is two-item agenda. One is that we'll be starting with revising or strengthening our basic concepts related to recurrence, and then we'll talk about the basics of graphs. We might not be able to cover graphs uh, in the complete sense in this session, so we will be holding another recitation session where we'll be completing graphs in the coming week. Uh, So let's start with something which we talked about while talking about functions and particularly numeric functions. So एक छोटी सी चीज है which we need to recap as far as the basic fundamental characteristic of logarithm is concerned. Let's revise that because we'll be needing that in solving some recurrence examples, and then we'll move forward. So if we start with the fundamental analogy of logarithm. So the kind of stuff which we did in the class was that, for example, if we have some rod whose length is 32 units and we cut this rod into half. So when we cut into half, we are left with two parts. One part is of length 16, other part is also of length 16. So we do the same thing for each of those parts or one of those parts. So for the sake of simplicity, I'm only moving down with one part. So with any of those parts, so when we have this part left with us, so we cut it into further half and we are left with this part. So the size of the part over here is, because it was 16, now it has been cut into two pieces, so its size is 8. We cut into half once more and we are left with this part. So size we are left with is 4. We cut it into two parts. The size we are left with is 2. And then we cut that part once more. And we are left with size 1. So in this case, we have done some process. We have initiated some process. We repeated it many times. And the same process has actually been repeated. So if you think of this whole thing as a mathematical function or as a programming function, the programming function is, or mathematical function is log. It's taking some integer as the input. And the kind of stuff which happens over here is that it cuts that x into two pieces. So for example, if it divides length of x over 2, and then it calls the same function once more on the new input. So the process is repeated on the modified input, which is half of the previous input. But as we are saying that we're stopping at this point, so that means that we need to have some stop criteria. So if you recall recursion or you recall induction, so in both of the cases, we used to have some base case. Base case essentially tells us the simplest possible situation which can be conveniently answered. So if length of the rod is 1, we just stop, right? So I'm not writing a perfect C++ code. I'm trying to write some pseudocode. So by stop would mean that we can call some return statement which will stop further execution. And if that's not the case, then the else part is that we do the same thing for half of the original input, and this thing keeps on going. That is the kind of logic which is happening on the right side of the screen, which is our visualization. So if we have to count that how many times this function has been loaded into memory, we know from our basic recursion concepts that whenever a function is called, it gets loaded into memory. So for each possible call, it gets loaded into memory, into an independent memory space. So, and like mathematical version of the same thing is that if I count number of cuts, or if I count number of divisions, which took me from 32 to 1, so the number of divisions were, the first division was performed over here. So 1, 2, 3, 4, and 5. So after 5 divisions, we reach to the base case where we stop. When we are into the base case, that means that we are no more calling the same function, right? So that this analogy or this intuition of dividing a rod into two pieces as we go along, this gives us the fundamental understanding of logarithmic function. So log of 32 with base 2 is 5. In other words, the number of divisions of dividing 32 repeatedly into two equal halves, then until we reach to 1, that those number of divisions are 5. Right. So let me do one more quick example, and then we'll like focus more on the kind of stuff which we are talking about. So for example, if I have to compute log base 10 of some number, which is, let's say, 1000. So when we say base 10, that means that the now rod size is 1000. We need to cut it into 10 pieces. So base is actually telling us that how many pieces do we need to create when we are going to do this kind of stuff, right? So if it is 1000, so let me count it 1, 2, 3, 4, 5, 6, 7, 8, and 8, 9, and 10. So we discard most of the pieces. We only continue with one piece. So this piece has now length of 1000 over 10, which is 100. And we cut it into 10 once more. So when we cut 100 sized rod into 10 pieces, we'll be left with something whose length is 10, and that will define our base case. Not really the base case, but if I do it once more, if I divide the rod of size 10 into 10 pieces, that takes us to the unit size where size of each rod is 1, and that defines the base case. So the number of divisions which we have performed from 1000 to 1 are 1, 2, and 3. In other words, log base 10 of 1000 gives us a very good visual analogy of being 3. Now we are going to have a look on the same thing in a slightly different way. And that is that if I rewrite that expression of log of base 10 of 1000, so this thing can be written as log of base 10 raised to the power 3. So from the fundamental properties of log, what we know is that log of x, where x is the base, x raised to the power y is y. And why is that the case? So if we like recall some, so what we're doing over here is that we have log of some arbitrary stuff, so a raised to the power b. So this gives us b times log of a with the same base. We are applying this formula over here. So y times log of base x with x is y times 1, because so if we compute log of 10 with base 10, the answer is 1, because we need one division to land to 1. So this is y times 1, and that gives us y. So we will be using these fundamental principles of log in our recurrence stuff. So that was the part where we want to have a quick look at the fundamental properties of log. We'll be applying them and using them as needed as we go along. So let's start with the problem of tower of Hanoi. So the problem is that we have three towers, three vertical towers. The first tower contains n disks, and those n disks are pre-sorted disks in such a way that the smallest disk is on the top, largest disk is on the bottom. Our task is, we name those towers, our task is to move all the disks from tower A to tower C. So the condition is that at one time we can move one disk, and in no state in between during that entire movement process, we should maintain that order. In none of them, smaller disk can go below the larger disk. So in the first step, what we do is that we move the smallest disk from tower A. So as we move the smallest disk from tower A, so let's say we take it to tower B, that was the smallest one. Now what we do is that we take the second smallest disk from tower A to tower C, which is empty. So in none of these two initial movements, we have violated any condition. So the second smallest disk goes over here. So now if you look at the current state, all those three towers are containing three different disks. So the only possible movement, one possible movement is that we undo the recent movement, which is that we send the disk from tower C to tower A. The other possible movement is that we move the first disk, which we placed at tower B. We move it from there and we place it on top of the second disk. So now tower C contains two disks in the sorted order, and tower A contains only one disk, which is the disk at the bottom, which is the largest disk. Okay. Now, if you like, because we are trying to focus on computing the number of possible moves which we need to carry out during this entire movement process. So if the number of disks on tower A would have been n, then n minus 1 disks have been shifted to tower C. So some number of moves, because these are n minus 1 disks, so number of moves which are required for n minus 1 disks, those have already been performed, and that's what is like stored. The kind of stuff is stored in tower C. So if we use this variable of capital H subscript n to notate number of moves required to shift n disks from one tower to another. So if n would have been 3, then like n minus 1 would be 2. And we, for a smaller like value of n, we can compute these we can compute these moves a little conveniently. Okay, sorry, I didn't have a look at the text stuff. So okay, yeah. So the question which we had about the logarithmic stuff, so it's not a like perfect power. So we can like deal with those things a little bit, but at the moment we are like we were trying to build the analogy that what does log mean, right? So we can fine tune our concepts related to the stuff which we were doing over there. Please explain n minus 1 wali cheese. I'm about to explain n minus 1 wali cheese into n plus 1. You are also right. We only showed this for n is equal to 1, right? What we need to perform induction on this? No, yeah. Okay, so just give me a few more minutes. I hope it will clear. So the reason I actually started with 3 was that I wanted to recap the sense of tower of Hanoi, that how those movements actually work. So now if you look at this visualization, which we have worked for n is equal to 3, that means that we are left with only one disk. Just imagine the situation if our tower would have been containing only one disk, then the number of moves would be 1. So if my task, if forget about tower C for a while, if tower A contains only one disk, my task is to move all of them to tower B. So what I can do is that I can move this largest disk to tower B, and I can remove it from tower A. So the number of moves of moving the only one disk is 1. So for 3 disks, we can, or for 2 disks, we can compute some moves which are more than 1. But what if the number of disks would have been n? Then in order to estimate the total number of moves required for moving all disks from one tower to n are notated as that like the simplest thing is 1, that the number of moves to move the bottommost disk is 1, which we have just moved from A to B, plus we need to have some hn minus 1 moves. So we have moved n minus 1 disks, top n minus 1 disks from tower A to tower C. So hn minus 1 represents number of moves required to move n minus 1 disk from tower 1 to another tower. Now, our final task is that we eventually want to move these remaining disks to tower B so that they are on top of the largest disk. And for that purpose, this time we'll be using tower A as an intermediate tower because we can't move both of the disks together and we can't place a larger disk on top of the smaller disk. So if I move the smallest disk from here, so I place it in tower A temporarily, and then I move the second smallest disk from tower C. I place it on top of the largest disk, so it comes here. And now we can bring this disk over here, right? So as a result, we have made another hn minus 1. Sorry, this should have an n minus 1, the previous one. Let me clean it up. So this was hn minus 1, and another hn minus 1 is required. Hn is number of moves required to move n disks from one tower to another. So hn minus 1 is number of moves required to move n minus 1 disk. Why we are putting them twice? Because in the first go, we put them into a temporary tower, which was C in our case, and we wanted to move the bottommost disk to the empty tower, which was B in our example. Now, once we are done with that thing, so first 1 plus hn minus 1 moves have been already done. So in order to bring the disks from this part over here, we need to spend an additional hn minus 1. So this in summary, this part gives us the expression that hn is 2hn minus 1 plus 1. Okay. So let me have a look at the comments now. One is for moving the biggest disk to another tower, yes. I think we have addressed rest of the questions, right? But if I missed something, so you can interrupt me, right? So just switch on your mic and you can start speaking. So if it sounds okay that this is how the expression will be looking like, that hn is equal to 2hn minus 1 plus 1. For what kind of n? So if n is greater than 1, which means that if we have more than one disk, then we'll be applying this expression. But what if we have only one disk? One disk can be conveniently moved in only one step. And in that case, we just write it as if n is equal to 1. So then hn is going to be equal to 1. So this expression gives us this is what we call recurrence relation. And this expression essentially captures the number of moves required to move n disks from one tower to another tower. Right? So yeah, so essentially we're like, so A, B, or C like don't really matter much. So the point is that one tower contained all the disks at the start. Rest of the two towers were empty. So we have moved n disks from one tower to another one. So how many moves are required? So the number of moves or the problem has been decomposed in terms of its moves to sub-problems. And some problem is that we divide the problem into two parts. The first part contains top n minus 1 disks, and the bottom disk is left alone. So that is moved conveniently. And we keep on applying that divide and conquer strategy. We keep on breaking down the problem into smaller pieces until we reach to the simplest case where we know the answer. Now, the point is, because this expression, if you look at this expression, the reason we call it recurrent or recurrence relation is that hn is being computed in the form of another hn. So h is the number of moves, on some number of disks. So in order to figure out number of disks, number of moves for n disks, we need to figure out number of moves for n minus 1 disks. So answer is not like very obvious or clean. So if I rewrite this expression over here, so the one which we have derived so far is hn to hn minus 1 plus 1 is the recurrence relation, is the expression which gives us that for any larger number of disks, this is how we'll be computing the number of moves. Now what we do is that what if we would have it having hn minus 1, what would be hn minus 1? Which means that if you are only interested in computing the number of moves of moving n minus 1 disk, we'll be applying the same formula. So this will become 2hn minus 2 plus 1. So now this part is going to be substituted over here. We'll move it there. So this the upper expression will look like 2 times two hn minus 2 plus 1 plus 1. So this plus 1 is coming from the previous expression. This 2 is coming from the previous expression. So we have plugged in value of hn minus 1 as this value. So now the expression is still like open. Hn is dependent now hn minus 2. So what would be hn minus 2? So if we try to compute hn minus 2 using the same recurrence relation, it will be looking like that hn minus 2 is 2 times hn minus 3 plus 1. So we'll borrow this expression and we plug it in the place of 2h minus n minus 1. So before I plug it in over there, let me try to simplify the first one a little more. So if we open up the upper expression, that looks like 2 times 2 hn minus 2 plus 2 plus 1. So 2 is getting multiplied with both of the terms inside the parentheses. So now if we what does it mean? It can be written as 2 raised to power 2 hn minus 2 plus 2 plus 1. So if I move one step down, and you can play around with this thing on your own as well, that if I substitute the value of hn minus 2, that will be 2 square times 2. So this the first power of 2 will become 3 hn minus 3 plus we'll be having what we'll be having over here inside the parenthesis. Square, this will be looking like hn minus 2 plus 1 plus 2 plus 1. So if you open it up, this will be 2 square. Sorry, I missed this 2 over here. So this will become 2 cube hn minus 2 plus 2 square plus 2 plus 1. Now, if you see at this bottom expression, there is a pattern which is evolving from here. And this should have h minus n minus 3 because we substituted value of h n minus 2 with its equivalent expression. Okay, take a moment. If there is any question, please interrupt me. So the last two terms are actually also powers of 2, 2 raised to power 2, 2 raised to power 1, and the last one is 2 raised to power 0, which is 1. So now if it keeps on going down, so after some k steps, it should be looking like 2 raised to power k hn minus k plus, so if you look over here on the first power of 2, that is 3. And the terms which are getting added towards the tail are starting from 2 raised to power 3 minus 1. So the kind of stuff which will be added up over here is 2 raised to power k minus 1, and it will go down to 1. So this is the kind of expression which is evolving from here. So different powers of 2 are getting added up over here. So the question is, what would be the last power of uh, 2? Or in other words, what would be the step where hn minus k can be substituted with something whose answer is convenient? So if we recall the first expression, we said that hn or m can be 1 if m is equal to 1. In other words, h1 is equal to 1. So as we can see from this pattern that first term was n minus 1, then we had n minus 2, then we have n minus 3. It's going down. So eventually there will be a point where it will reach to h1. So let me go to the fresh screen. So the expression which we have landed on so far looks like this. Hn is 2 raised power k times hn minus k plus 2 raised power k minus 1 goes down to 1, which is 2 raised power 0. Now, so it has to go further down. So we need to reach at a point where this h term becomes h1, where this term becomes h1. So in order to make it h1, we need to have over here n minus n minus n minus 1. So k goes down to n minus 1. That will be the point. So in that case, when k becomes n minus 1, if you look over here at k, so the first power of 2, which is the coefficient over here, will become n minus 1. And then it will be going down to 2 raised to power 0. So we know the answer of hn minus 1. So we can substitute this thing with 1 because now this hn, this is h1 actually. So this expression will be looking like n minus 1 plus n minus 2 and goes down to 2 raised to power 0, which can be written as summation of I is equal to 0 to n minus 1, 2 raised to power I. And now this part is actually representing a finite geometric series. You can apply the basic formula of finite geometric series over here, which says that summation is equal to, so according to the formula, this summation should be equal to A times 1 minus Rn over 1 minus R. So A is 1 over here. So 1 minus, what is the common ratio? Common ratio is 2. So this will be 1 minus 2 raised to power n over 1 minus 2. And this will give us minus 1 plus 2 raised to power n. And we can write it as 2 raised to power n plus 1. This is what we call the closed form. And this is a closed form of the recursive formulation of tower of Hanoi, which represents the number of steps or number of moves required to move n disks from one tower to another tower. Okay. So if things are like making sense, so let me go over one more example of recurrence. And again, we are trying to originate things from our algorithmic perspective. So if you recall the programming days, some of you might be conveniently able to recall if you have coded that thing, or you might have coded that thing in CS200 as well. But if not, so one search algorithm is called binary search algorithm. So binary search algorithm or binary search program expects that we have an array of size n and all elements in the array are sorted. We have been given another element, which is the key, and our task is to locate the index of key. So the algorithm suggests that find the midpoint of the array. So as you find the midpoint of the array, because the array is pre-sorted, so if the ideal case is that this is your key, so compare the midpoint against your key. Okay. Question is, can you explain how we got the yellow line in the previous example? Can you please, like, because I forgot the colors I was using for different purposes. So, what did yellow line talk about? So, if you can mention that what was in the yellow line, I can restart from that point. Yeah, sure. So, okay, so we'll let me go one step back. So Hn was looking like 2 raised power n minus 1 H1, and this summation was going down to 2 raised power 0, which was our first thing. So are you okay with this substitution? Or do I need to like go one step? Okay, so if you are okay with this thing, so we actually summarize this part as a summation. So H1, so I can write it because H1 is 1, that's our base case. So base case says that H1 is 1, so this becomes 2 raised power n minus 1 plus 2 raised power n minus 2, and these powers go down to 0. So now if you look at the powers, they are starting from 0, they're going up to n minus 1, which means that our index is starting from 0, goes up to n minus 1. So there are things which are getting added up over here. All of them are powers of 2. So we can generalize it as 2 raised power I, where I starts from 0 and goes up till n minus 1. So are you okay till this moment? Okay. So what we did was that we wrote it as summation I is equal to 0, n minus 1, 1 times 2 raised power I. So each new term is getting we are getting each new term by multiplying 2 with the previous term. So if you look at this expression, so this defines the geometric series, finite geometric series. So where this part is the first term is 1, and 2 is the common ratio, which we call R. And we simply apply the formula for finite geometric series. So apply that formula and you should be able to land to 2 raised power n minus 1. Okay, good. So now going back to my research, so we have been given an array of size n. We are figuring out where is the key. So we compare the midpoint with key. All elements on the left side are smaller than the midpoint. All elements on the right side are greater than the midpoint. So if our key is not equal to the midpoint, then it is either smaller or greater than the midpoint, which means that because the array is sorted, so we can limit our subspace to half of the array. We don't need to, for example, if key is smaller than the midpoint, then we don't need to look at the right side of the array. So we'll only be performing remaining steps or remaining processes on half of the array. So we cut the array into almost half, and we are left with some smaller size, which is actually proportional to half of the array. So we do the same logic again and we compute the midpoint. If this is the key, then fine. Otherwise, key is either on the right side or the left-hand side, depending on its relationship with the midpoint. If it is greater than the midpoint, then it has to be on the right side. So for assuming that it is greater than the midpoint, then it won't be on this part and we'll be confining our search space to this part. So we'll keep on doing this thing repeatedly or recursively until we reach to something whose size is 1. So we are left with array of size 1. If it contains the key, we are fine. We'll return its index. If it does not contain the key, we will return something which will represent failure of the search process. For example, we can return -1 as the index that to notate that key is not there in the array. So now the point is that if you compute the number of steps which we have performed while starting from that point going down to 1, this is somewhat very similar to what we saw, that we started with size n. We were n over 2, we went to n over 4, we kept on dividing the array over 2. We have been cutting into halves and we landed down to 1, which is the smallest or trivial most part of the array. That means that if array is of size 1, we don't need to do further processing. So either we got the answer or we need to stop. So if you recall the starting discussion where we talked about logarithm, so the number of steps which will be performed from top to bottom are going to be log base 2 of n. Base 2 is coming from because we are cutting the array into two halves at every step. And that's the reason we'll call it binary search. Now, if you recall the code which is on the slides and you might have already coded it, there might be some constant number of additional steps, some constant number of additional if conditions, or some other few lines of code which you might have written inside that recursive definition of the function of binary search. So if our task could have been that we want to compute number of comparisons required to perform search in an array of size n. So we notate it as Tn. So Tn is notating number of steps which are required to perform on an array of size n. So we need to compute, we need to formulate its recurrence relation. And so if you like do it like this, so it can be actually depending on the actual code which we'll be looking at, and there is an actual example of some pseudocode on the slides as well. So without looking at the code, we say that we perform number of steps to half of the array, Tn over 2, plus some constant number of fixed lines written in the function. C is notating some constant, which we perform every time we call the function. So for example, we compute the midpoint, that's one line, there's another if statement which checks whether it's key, there are two more if statements. So 4, 5, or maybe 10, whatever are those number of lines, those are representing some constant steps. Let's first try to understand this expression. This expression says that the number of steps required to search an element in an array of size n is notated as Tn, and it can be formulated recursively as, because our function is recursive, there is the cost is the number of steps or number of or maybe amount of time required is dependent on the same thing over half of the array plus some constant number of steps. So now, what is Tn over 2? So if we use the same formula, because in Tn over 2, our algorithm is not changing. What is changing is the input size. So if input size is changing, so this algorithm will give us T of n, we'll further half it. So half of n over 2 would be n over 4 plus C. Now, somewhat very similar to what we did in case of Tower of Hanoi example. So we'll plug in this value of Tn over 2 in the first expression. So this thing will become Tn over 4 plus C, and the previous C will remain as it was. So we can write this whole expression in a slightly simpler form, and that is that this is n over 2 raised to power 2 plus 2c. Now, what is T of n over 4? T of n over 4 would be half of the input, Tn over 8, number of steps required to process half of the input plus constant number of steps. We'll plug in this thing over here, and our expression should start looking like this. It will be T of n over 8 plus C plus previous two C's. And we can simplify T of n over 2 raised to power 3 plus 3C. Now, if you have been with me till this moment, so I'm taking this bottom expression to the first line, and we'll evaluate it further. So it will be looking like this, that T of n is, so the kind of stuff we've done so far is T of n over 2 raised to power 3 plus 3C. So if we like dig little deeper, so it will be looking like Tn over 2 raised to power k plus kc. So there is 3 here, 3 here. So 2 raised to power k plus kc is the generic expression. But we want to get rid of this t thing from the right hand side. So how can we get rid of this thing? So if you recall the binary search algorithm, that says that if your size of the array is left with only one element, if you have only one element in the array, then you don't need to perform further steps. Your answer is one. The number of steps required, number of further steps required to process an array of size one is one. So in other words, we are interested in something such that this part, let me try to change the color, such that this part lands down to something which is t of one, because we know the answer of t of one, which is one. So what does that t of one mean? That means that we want to do something which should give us t of n over n. So, but if you look at the denominator over there, that is 2 raised power something, right? So what would be the power of 2, which will give us n? In other words, how many times we need to multiply 2 with itself to land to n? So this is something which we have already figured out. This is something very similar to that if we had n, if we keep on dividing that n over 2 again and again, in how many steps we landed to 1? That answer was log n. So this was log of n. If you think of this whole exercise in the bottom up question, start thinking from bottom to up. So in how many steps, if I start with 1, how many 2's do I need to multiply with this one repeatedly such that I land to n? So the number of times I need to repeat 2's together to land back to n is same as this one, which is log n. So 2 raised power log n, which means if I keep on multiplying 2 log n times, that will give me n. Why we are like interested in this thing? Because we are interested in something. You look over here, we wanted to get t n over n. And the part which we had over here in the denominator is in the form of power of 2. So we are actually interested in something t of n over 2 raised power log n. So let me like rewrite this whole thing in a little cleaner fashion. So we wanted to we keep on going down until we reach to t of n over 2 raised power log n, which means n, that will give us n over n, which is t1. So what would be the coefficient with or the term which will be getting multiplied with c? So when power was k, it was k getting multiplied. When power was 3 of 2, power of 2 was 3, so we're getting 3 multiplied with c. So over here we'll be multiplying log n with c. And now what is the first part? So this part is essentially, this means we are talking about t of n over n, which is our base case, which t of n over n means t of 1. So, and t of 1 is 1. So we'll substitute this whole thing with 1 plus c times log n. And this expression is now the closed form of t of n, or it gives us the number of steps which we can compute without doing that recursive process. We do it for some given algorithm, whose number of steps are like changing at a very fast pace. And by fast pace, in our context, we mean that they are changing logarithmically. So can you explain why 2 to the power log n? Will it be log is 2 n? Yeah, sure. Let me try to explain. So I hope we are okay with this part. So I'm going back to that thing, that why did we probably do this step? So why this thing is what we are interested in, and why this is equal to n? So I can explain it once more. Okay, so first think of that what was log. Log was that if you have been given some number, so let's say we have been given 32. So we cut it into half, we are left with something which is 16. We cut into further half, we are left with something which is 8. We cut into further half, we are left with 4. We cut into further half, we are left with 2. We cut into further half, we are left with 1. So how many cuts have been made? 1 cut, 2 cuts, 3 cuts, 4 cuts, and 5 cuts. In other words, log of 32 with base 2 is 5. Now, The question has changed. Question has flipped. Question is that we want to construct 32. We want to land onto 32. What power of 2 will give us 32? That's what we want to compute. In other words, we are interested in something which is the reverse process of this first step. We are here. So our initial or global product is 1. We multiply it with 2. We multiply it with 2 once more. So 2 multiplications. We multiply it with 2 once more. 3 multiplications. Multiplied with 2 once more. 4 multiplications. Multiplied with 2 once more. 5 multiplications that will give us 2. Or in other words, so this is 2 raised to power 5 equals 32. So what is 5? What is the relationship of 5 and 32? So that's what we have figured out at the start, that 5 is log of 32 base 2. So we can write that thing as 2 raised to power log base 2 of 32, and that equals 32. Or in general, the kind of stuff which we used in our derivation was that 2 raised to power log of base 2n is n. So does this clarify your last question? The question was that how did we land to n? Yeah, you're right. So we'll be using base 2 to be precise, but we'll be using this kind of stuff a lot in your coming course in the next semester, which is data structures. And over there, you will study another notion, which is called asymptotic notion of studying complexities of algorithms. And you will see that the bases don't matter much. So in our computer science life, if we like don't worry much about the bases, that's also okay. But your answer is fine that I'm talking about base 2 to be precise over here. And you might have seen that visualization that the way we have constructed 32 in the bottom up fashion, that how many times we need to multiply 2 with itself, that gives us the like sort of inverse process of what we were doing at the start while computing log. Right. So for precise computations, you are absolutely right. But in the long run, while you stay in your computer science journey, you won't have to worry much about the bases, because you'll see eventually that roughly speaking, they are equivalent. They are not exactly equal mathematically, but in a computer science life, they will be treated equivalent to each other. Okay. So we're done with the first part, which was related to what we call recurrence relation. So this method which we have used over here is what we call substitution method, because we substitute the values repeatedly until we land onto the base case. And that's exactly what happens in the computer's memory while computing the answers of a particular function. So if you write some recursive function like binary search or Fibonacci function or factorial function, you write them recursively, so each recursive call will keep on getting loaded into memory. And once you reach to the base case, then you start rolling back. Right. And the alternate method, which was the first method which we talked about in our lecture slides, as far as the recurrence relation is concerned, that was that we were guessing an answer, an expression, and proving its correctness by using induction. So that was relatively simpler. But like substitution method might have been a little trickier, particularly in the logarithmic cases. And I hope it made some sense. So now in our second part, we are moving to a quick revision of graphs. I'm not worrying much about graphs at this stage, because we are still in graphs, and we'll be like with a lot of hope and prayers that you'll be joining on campus from the coming week. So we'll be having an on-campus recitation session where we'll be like doing all things related to graphs, and we'll be doing, but like for the next few minutes, let me spend some time on fundamentals of graphs, and then we can stop and we can talk about anything you would like to share. Okay. So from the computer science perspective, graphs are very important structures. We call them discrete structures when we study them in discrete math, because over here our focus is not based on the implementation. Our focus is not to store data inside those structures, just like sets. So when we study sets in discrete math, we talk more about the properties of sets, the kind of stuff that we can do with sets. But as you study sets in data structures, over there you store data inside sets. Same is the case of graphs. When you study graphs as data structures, you'll be implementing them, you'll be coding them, and you'll be using them as data containers or data structures. Over here, we are studying them as discrete structures. The reason they are discrete is that they are actually composed of two discrete components. So each graph is composed of a set of vertices and set of edges. So graph is a pair of which contains two sets, which is set of vertices and edges. Those are the kind of fundamental things which you have already seen in the lecture slides as well. So so we talked about two types of graphs. We might be having directed graphs and graphs might be undirected. So we might be having undirected graphs. So when we say directed graphs, that means that between every two edges, there must be, if there is an edge, that must be directed. So which means directions are explicit, and that's why the name directed comes from. That's where it comes from. For the undirected parts, we can have a line segment between two vertices. That means that those two kind of vertices are connected, but the direction does not matter. So for example, if both of those graphs are representing some map of the city, and the first one is location A, other one is location B. So the first one, the directed graph in this example says that you can travel from A to B, but you can't come back. So the return is not allowed. But in the case of the undirected graph, you can go from A to B, and you can, using the same path, same edge, you can go from B to A. So that's the kind of luxury which we have in undirected graphs. We can't really say that which of them is more important, which of them is more useful. It totally depends on the kind of application which you want to build, and you want to use graphs as your underlying structures. So the last component which I had planned over here was that how graphs are represented in memory. So we have two implementation choices. One choice is called adjacency matrix. Other one is called adjacency list. So matrix means that we have to use the two-dimensional array in terms of our code. So for example, if we have three vertices, we have a graph like this, and let me keep it directed at this stage. So there are vertices A, B, C, there are edges between them. So our matrix contains columns titled as names of vertices, and same goes for rows. So there's no direct edge from A to A, so our diagonal will remain 0. So there is an edge from A to C, so we mark an attendance of that edge as 1. As there is no edge from A to B, we mark its absence using a 0. There is no edge from C to A, there is no edge from C to B, so row of C is marked with zeros. There are edges from B to A and C, so both of those entries are marked as ones. So now if you think of the size of adjacency matrix, or the amount of memory which we are occupying over here, that is, if we think of the set of vertices as a set, think of set of vertices as a set. We call it capital V, take its cardinality. So square of that cardinality is the size of this matrix. Now, adjacency list says that we create a list of all vertices first, and then we append only the immediate adjacent vertices of A. So C is adjacent to A, so that will come over here in the list of A. B is not adjacent of A, which means there is no direct edge from A to B, so B won't come in the list of A. But if you think of B, we can go to A directly from B, we can go to C directly from B. In other words, A and C are adjacent to B, so we put them over here in any order. So this order does not matter. We can write them as A, C, or we can write them as C, A. So there is no vertex which is directly connected with C, so that list is empty. So I'm just notating that emptiness as a cross or nil. So now if you look over here, the amount of memory which you have occupied over here, or the number of storages which you need. So we needed 1, 2, 3 spaces over here, 1, 2, 3 other spaces over here. So these first 3 spaces are essentially representing size of the set of vertices. And the second component, which is this part, is coming from edges, because each edge is making us create an object more specifically, or create a box over here, or create an entry over there. So that means that the total number of items which we need to store, or size of the adjacency list, is going to be V plus E. And the size of the adjacency matrix is going to be V squared. So, okay, now there are 2 comments. For the next recitation, can you please discuss graph questions that involve proofs, like for example, which involve proving a disproving statement based on knowledge of graph? Sure, I can definitely do that, and I think because we are focusing more on recurrence in today's session, so in the next session we will be only focused on graphs, and we can get deeper on the proofs part as well as far as graphs are concerned. Is it correct to assume lists are similar to linked lists? This is absolutely correct. So the question, because the question was only sent to me, the question is a beautiful question. I'm not sure. Like, it might be the case that the person who posted the question is aware of this thing, or if you have studied that kind of thing in CS 200. So I actually wanted to avoid that term. So each of these lists is technically a linked list. So we are actually creating an array of linked lists. So if you are familiar with linked lists, so each row is a linked list. More specifically, we're talking about an array of linked lists in terms of our implementation. That's exactly what is the adjacency list. But because we are not like worrying much about the implementation part in this course, so that's why I didn't term that linked listing. But in data structures course, you will definitely be using linked lists to implement adjacency list, or when you'll be facing those graph related assignments, if you like decide to do those assignments on your own, and you don't choose GPT for that. That was on a lighter note. Okay. So that's it. I'm stopping the recording, but if you would be having any other questions, we can talk about those questions.